Hello and welcome to another video where I'm going to talk about C++. This is not something that I've done before, but something that I've always wanted to do. So I'm just going to go about the motives of these series of videos. I'm probably going to make 2 or 3 videos on this. And yeah, the thing is that I was reading this blog, enforcing signatures on template callbacks from Philippe Groarke, if I'm pronouncing that correctly. So the whole premise of this blog is that you often want to pass callbacks around, pass them to as parameters to functions, and there are usually a bunch of ways you could do it. He mentions 3 of these, and of course, this did function one is slow. It enforces the callback, however, the signature, however, and there's the function pointer, which also enforces the signature. However, it does not accept object functions like any object that has an invocation operator implemented. So you can invoke those objects. And there's, of course, the one that I've always used that does not enforce any signatures. And he is correct that this somehow, sometimes, not almost always gets confusing. You start forgetting what the signature was. You need to go and check some examples on what the signature should be. So he tries to kind of get the best of 2 worlds. He wants to implement some type that could enforce while getting the callback as a template parameter. So to go further into this, I've actually tried to implement something better because I wasn't content with the implementation. I will talk about the shortcomings of this implementation upcoming videos, but to understand those, I would like to first talk about what things are actually callable. So in C++, we have a bunch of things that you can call. Of course, starting is a function. So that would be like in foo, you take some parameters in, let's say maybe a const char pointer, maybe an int, a double. So this is the first thing that comes to mind when you think about things that you can call. So we can actually call this here simply by invoking it. And I'm going to return the value. Let's return something here. Maybe 10, who cares? Let's give it a const char pointer, some integer value, and some double value. And this should compile just okay, and the program return 10, as we expected. So this is the simplest thing that we can actually call. However, things don't stay that simple for long. Let me just fix that formatting. We start having these things called function pointers. So I can get a function pointer, like let me use auto for this, const auto, and footer. I'm gonna call it footer, and I'm gonna get pointer to foo. And now I can call this footer instead of foo. And it should probably give me the same result, as we can see. So let's dig in more into what the signature of this thing is. So the signature of this would be like so. You have a foo pointer, and the return type is here. I'm going to remove this const and put it probably here. And then we have our parameters. The type of our parameters will go here. And this should probably do the same thing. I'm just gonna try to prove you that I've placed the const in the correct position. I haven't tried this. I haven't prepared anything for this, so I could be doing something stupid. and I will try to like kind of speed up things if I'm doing something stupid for long. So here it says that footer is read-only because of this const, and if I remove that const, things should go okay. So I'm gonna keep this const for now, and this is our footer. Now I'm going to introduce, okay, I should stop control S-ing. I'm going to introduce function references because there are other things that we encounter in the wild. So this is a function reference. This is virtually not really any different than what we had there. Than footer. Fooref is not much really different than, I'm going to remove that, than footer. And just as you would assume, a reference is just an alias. So when I try to assign foo to fooref, I'm going to get read-only reference. Right? So these are the derivatives that we get from functions, function pointer and function references. So these are three things that we have. There is one other thing that we have. This is the type of the function, the type of the exact function, foo. This is the signature of the function. And you can't really make any variables of these. You can just make functions. So we have three derivatives. One, you can't make any variables, which is you can make functions but not variables. We have function pointers and we have function references. Other than these two, we have objects that are callable. And for example, let's clear this foo structure, and you can write an operator, write an invocation operator, which would be operator blah blah. Let's make the signature the same, so we wouldn't need to bother ourselves much. And this can be int. All right, so this is our callable type, and I'm going to make an instance of it. Maybe I should name it better, not to mistake it with our foos. Bar, maybe I should have named better, but here we are. And I'm going to call bar. What is going on here? Okay, I'm not returning something here. Let's first return this. Return 10. Let's not return 10 to make to be a bit different. And while this is going wrong, operator, yeah. Okay. And I should just stop saving. So this just worked as we expected. And there's not much to say about this simple example, but things again will not stay simple for long. We can really modify this a lot because this is a member function, and as we know, member functions can access the class, and they can the class is like some other parameter that you pass to the member function. And that parameter can be overloaded on const, overloaded on a lot of things. So I'm going to write a bunch of overloads here to show you just these can be actually overloaded. So you can have overloads for R value references. This is an overload for R value reference. You can overload for L value reference. I'm going to give these different values so we can actually test them. And you can have it for const L value, and probably no reason to do this, but you gotta do what you gotta do. So maybe this. Let me give these different values so we can actually test them. All right, so we have a bunch here, and currently this overload is being selected. And let's try to change that. Let's try to make bar a const value. And if bar is const, we're invoking the const L value. I'm going to remove this and try to actually move bar. And what are we getting here? The move is not included. Yeah, I'm going to include utility. So sorry if this is getting boring, me typing, but I will try to kind of edit these. Let me see. All right, so we're getting this overload selected, and I don't know how I can't easily do that, but let's do it. Static cast. I'm going to static cast these to const R value, something dumb, but something that exists. Let's go right here. Can I do? Okay, yeah. Okay. So I'm selecting this. So as you could see, there is a bunch to overload. This you might think that is not really something that you will encounter in your real code. Probably you're correct, but you're going to support whatever you need to support if you're writing some generic code. So yeah. So that is one other thing that you can actually call in C++, objects. There is a few other, there's one more, I believe. I don't think that there exists anything more. And that would be pointers to functions, pointer to member functions. And that's a whole mess of itself. Again, I did not prepare anything for this, but I'm going to give it a try. So int my member function, and it returns 5. Let's copy these as well to keep the signature we want. And that's it. Let's try to get a pointer to function here, pointer member function here. And my member function, I'm going to put this here, const auto, and this is a reference to member function. Const auto ref mem func ref. And I'm going to try to call this, and that would be something like bar dot. Is that class? I should be. I'm not sure. Also, let me copy this. And here we go. Huh? What does it say? Has no member, blah blah. Let's do this. I don't think that is this. What are we getting here? To pointer. Let's. Oh, this is actually a pointer. This is not a reference. This is a pointer. And to call a pointer to member function, blah blah. All right, this is telling me that I need the parentheses here. And there we go. So this is a pointer to member function. And I could go about actually figuring out the signature of that, but I don't think that is something really important here. Let me just do this as well to see if I can get a reference to it. And what is it telling me? Invalidates of the static member function. All right, I'm not sure how to get a reference to member function, but I guess you get the point here. And so yeah, that is the whole shenanigans of things that we can actually call. And you would probably be by now be thinking to yourself that why did he miss lambdas? And I did not miss lambdas. Lambdas are generally uh, some some syntax that translates by compiler that is translated by compiler to an object type that has an invocation function. That as simple as that, nothing else. So bar here could just as well be a lambda. So nobody cares about lambdas. They're the same things. Okay, and that concludes everything that you can call in C++. But then the question arises, why are you passing these callbacks around so much? Why do you even care? So to illustrate why I would care, here I'm on C++17, there are many reasons to pass callbacks around. One would be threads. To run a standard C++ thread here, you would actually need to pass it something, pass the callback, pass the functions, some action that you need to do on some other threads. Let's give it a name. My thread here. This is actually being run. I don't think that this is going to correctly link with pthread, but whatever. So I'm going to pass this in lambda. This is one example where you actually need to pass lambdas around. The other example would be things like variants. To use a variant, you usually call visit, std visit. So let's say I have a variant here of, let's say, why am I doing that? Of, let's say, int or const char putter. All right. So my variant, what you would do is to use this variant, you would probably do an std visit. And there's reasons why I actually brought this up, and I will get to it soon. Let's do this. We're not on C++20. Let's make it auto my parameter. That's auto my param, and we do something here. Who cares? All right. So, and yeah, of course, we're going to pass the variant itself. Come on. There we go, and I did save again. All right, this is visit. This is just a visit. So if you actually take a look at these, here my variant is not going to be stored anywhere. It's not going to be copied anywhere. It's not going to be, its lifetime is not going to be managed by anyone. It is just something that is important to be available during the call to visit, and visit does not care about its lifetime. Its lifetime should just exceed that of the call to visit. And visit is not going to make a copy of this, is not going to manage its lifetime in any way. And however, this is not the case on my thread here. When you're constructing a thread, you're passing a callback, and that callback is going to get copied, get constructed however you want, in the by maybe move, by maybe copy constructed inside a member inside the thread. So there's going to be a copy or move here of our callback. However, here no copies, no moves, just forward and whatever you passed, and that's that. So this is actually where these come into play. You actually need to forward your callback here. Otherwise, if you don't forward your callback, you might actually choose the wrong overload here. So you give the callback to visit, and visit has to forward the callback you gave it before actually invoking that callback. Otherwise, you could just simply make a mistake and call to the wrong uh, operator, invocation operator. So yeah, that is the other point I wanted to make. So I guess I'm not sure for how long I've been talking here to my microphone, but yeah, I guess this is all that I wanted to say for this video. I will probably make another video and go through some of the issues, the implementation that we see in this blog has, and I will kind of go over my own solution for this and try to see which one lacks what and what are the advantages to each of these. Of course, I didn't find any perfect solutions. So if both this blog and both my implementation has its own issues. So each of these has its own issues. All right, that's it. Thank you for watching and see you maybe on the next video.